Let's take a look at elementary steps. We know what an elementary step is, of course. Let me preface everything by saying this. To organize your thoughts in terms of elementary steps, there are two types of interactions that govern elementary steps. One is acid-base reactions, and we covered that one last time. So if we have a weak acid and a strong enough base, you can drive the reaction. Or if you have a weak base and a very strong acid, you can drive the reaction. That's one way to look at it. The other is, and we're going to define our terms in a minute, right away actually, is electrophilic, nucleophilic interactions. Okay, so let's get to the slides, and these terms will come up in a second. We know that opposite charges attract each other and like charges repel. That's like grade school physics. When you're looking at possible elementary steps, if you don't have, well, actually, these two are sort of related. If you have an excess of electrical charge, if you have a full charge, like a negative, or if you have a partial charge, like the delta negative, but it's still a neutral compound, then that would be your nucleophile. In other words, it has excess electrons. It's looking for positive charges. And that's what nucleo means. It's the positive part of the atom. And then the electrophiles, let's see, this is the nucleophile. The electrophiles would be either this or full charges, positive charges. But if you have an excess of negative and a deficiency on the other side, then you have the opportunity for electron transfer and forming a bond. And that's what we're trying to show here with this hydroxyl and this acid. So we have an acid-base reaction, but we can look at it in terms of electrophile and nucleophile. Electron rich is going to attack the electron poor hydrogen and form that bond. That gives you the water molecule, and the other bond breaks. So those electrons have to be transferred to chlorine because it's more electronegative than the hydrogen. That seems fairly logical. Okay. Identify the electron poor hydrogen atom in methanol. All right. If we have this structure for methanol, and we're looking for the electron poor hydrogen, which hydrogen is closest to the more electronegative? That's this one right here, right? So this one is going to be slightly positive, and this is definitely going to be negative. We have a polar bond. So this is where the action is going to happen, right? If hydrogen's involved, then we're not interested in these guys over here. Let's see. Draw the mechanism by which methanol acts as an acid in a proton transfer reaction with NH2 minus. Okay, so NH2 minus, let me remove some of this stuff so we can draw our arrows in. NH2 minus. Normally, we would have a we would have three hydrogens. If it were ammonia, that's the way I look at it. If it were ammonia, we'd have three hydrogens and a lone pair. But we're missing a hydrogen, and that means this nitrogen is 5 minus 1, 2, 3, 4, 5, 6. 5 minus 6 is a -1. That means it's a -1 formal charge. Okay, so that's why it has the minus charge on it. And the only way to get that is two lone pairs. Okay, so which one's got the excess electrons? That one. And this one is deficient, right? So we're going to take these two, right? They're going to attack this positive, and then this bond breaks, and those electrons have to go here.
So there will be another lone pair on that oxygen,
Yes,
and then that hydrogen will go to the nitrogen.
right. This will form ammonia, neutral charge. Now this one is now excess, negative.
Gotcha.
Let's see. There it is.
These problems always make sense. Yeah,
Yeah.
this always
Yeah,
makes sense.
Yeah.
Right. Then when you go home, it's going to. Yeah, it takes practice. Okay, that has a name. The azonide anion. Azonide. Who thought that one up? Somebody with too much time on his hands. Okay, let's see. Anions don't exist in the solid or the liquid phase without the presence of cations. That goes back to general chemistry. When I said physics, they like to separate charges and make static charges. Chemists don't. When we have chemical reaction, it's always neutral overall. You can have positives and negatives in the reaction, but overall it's neutral. So whenever you have an anion, you got to have a counter cation. And very often these cations are just spectators. Right? For instance, lithium, sodium, potassium are good ones. The reason for that is because any alkaline metal salt is soluble in water and in aprotic solvents too. So what's the reactive species in sodium hydroxide? It's the hydroxyl. Okay, so draw the curved arrows, proton transfer, KOCH3 and HCN. Okay, so Lewis structures first. So if we're going to have KOCH3 and HCN, this one's going to be HCN with a lone pair. Okay, this one's going to be, since that's a spectator, this one's going to be CH3O. And this is a minus, so it has to have 3 lone pairs. All right. Proton transfer between KOCH3 and HCN. Well, this one doesn't have any protons available to transfers, so they have to come from this side. So one of these lone pairs is going to attack that one. Now we know that this is slightly positive because of the the electronegativity of nitrogen, but it's a triple bond, and that's effective negative charge, effective electronegativity. Okay, it's increased electronegative. So this side is going to be negative, this side is going to be positive, so it's deficient. All right, so we form a bond there, this one breaks and goes there. Negative charge on indicates this electron. Okay. What reactive species remains in solution? Should it be considered electron rich or electron poor? The negative charge on, no, not H2N minus. That wasn't a reactive species. HCN.
Right.
I don't know where that one came from. Oh, you know what I bet? That was my correction. I made that correction because the original slides that came from the publisher was wrong. Okay, let's see. Yep. attacks, breaks the bond, we're good. Well, and that gives us, let's see, this now is methanol, and this now is minus. Okay. What's an organometallic compound? Actually, they're very important in organic chemical reactions. And the reason for that is metals have a tendency to give up electrons very easily. So if you've got a metal atom bonded to an organic compound, usually through the carbon, it's going to want to give up an electron, at least one electron, to the neighboring carbon. And it makes the carbon negative and the metal positive. Now, for convenience, we often just remove the metal and keep the carbon because the metal is not going to be reactive. And that's why we simplified it to this carbanion, right? For any elementary step, just recognize that the reality is the metal's still there. That's just that being there doesn't affect the reaction mechanism. Yes, that's the whole point of that slide. Simplify for organometallics, which gives you a carbanion. It makes that carbon is now nucleophilic. It's looking for a positive charge somewhere, partial or full. Okay, this leads us to the concept of the Grignard reagent and other organometallics. They promote chemical reactions by producing those carbanions. And I'll say this, chemical reactions in which the functional group changes, like an OH changes or an NH or SH attached to it, those were fairly simple reactions to master in early years of chemistry. Forming carbon-carbon bonds, new carbon-carbon bonds, those were the ones that took some work. And one of the ways we do it is with organometallics. We make that carbon is now electron rich, so it will attack an electron poor carbon and form a bond. That if you set up the reaction conditions correctly. So they're not competing reactions. But we haven't got to that point yet. Talking about competing reactions. Actually, we're not going to get to that. That's second semester. But this will give you a taste anyway. Okay, so organolithium compound. So we have this lithium attached to an ethyl group, and we simplify it by calling it a carbanion with the electrons from the bond of the lithium transferred to the carbon. So by simplifying, what we're actually doing is we're saying this, right? And this one comes off as a positive spectator. And then we're left with that lone pair and negative charge. That's how we simplified it. The Grignard reagent is usually an alkaline earth and a halogen. So we put the metal attached to the, in this case, we've got, that's pretty sorry. We've got the metal attached to the carbon, but we add a bromine on here. So what's happening? Well, the magnesium wants to give up its electron. Okay, this is going to be difficult. I may have painted myself into a corner. I want to end up with this. Right, I want to end up with that. Bromine, this probably wouldn't work as well with chlorine or fluorine because they're more electronegative. But bromine is a big halogen, has lots of electrons available. And I think it makes more electrons available to make this carbanion. Lithium, well, now we've got lithium and copper involved, right? What happens then is we actually break both bonds and make a methyl carbanion. Simplifying things. Okay. So remember the definition of reduction and oxidation, right? Reduction is anything that's reduced has acquired electrons. Anything that oxidizes lose electrons. Okay, so if we want to provide a reducing agent, we need something with excess electrons that are very willing to give them up. That makes it reducing. It has to be more, it has to want to give up those electrons. And when we simplify this lithium aluminum hydride, which is a common reducing agent, or sodium borohydride, which is another one, we simplify those in elementary steps as the, I don't know what you call it, hydrogen anion. Those hydrogens are extra negatives. Yeah. Okay, that's right now we're just talking about simplifying before we get into reactions, which we're going to do right now. Okay, we want to define our terms as we go. If the reaction is bimolecular, remember the discussion of molecularity in second semester, I think it was, general chemistry. Molecularity refers to how many molecules come together in a collision for a reaction. And remember, the term molecular is almost not heard of ever, because 3 molecules have to come together at just the right energy, just the right orientation to make the reaction go. Probability is infinitesimally small. So it's either unimolecular or bimolecular. And that's where we're sticking with that for organic reactions. This first one is bimolecular, and that's what the 2 stands for. Oops. Let's get another marker here. The 2 stands for bimolecular. Okay. The substitution is the nucleophile bonds with some part of another molecule we call the substrate and kicks off a leaving group. Okay, so that's a substitution. We're taking that hydroxyl and we're substituting it for the chlorine. Okay, so that's where the S comes from. Substitution. And then it's a nucleophilic substitution. In other words, the excess electrons in the hydroxyl in this case is a nucleophile. It's looking for something that's electron deficient. And chlorine has lots of extra electrons and it's electronegative, so it's causing that carbon to be slightly positive. So we get the attack from the nucleophile on the carbon and the chlorine, and the bond breaks and the chlorine leaves as a negative charged species, and we get methanol as a process. This is a bimolecular. So what happens is this elementary step occurs in one fell swoop because both of them are acting together the bimolecular reacting together in a nucleophilic substitution to give you a product. Now, I will say this. How do you tell if you've got a reaction that's going to go, right? Whether it's this one or it's any of the other three that I'm going to give you in a minute. You look at the leaving group. Is that a stable leaving group once it's left? Chloride ion, oh yeah. It's got a full octet. It's negatively charged. It's very electronegative. That chloride ion is very stable. So that's a good leaving group. Okay. Another example here where we have methyl sulfate, I think is what you call that. We have the nucleophile as ammonia, right? Is that carbon electrophilic enough to attract the attention of the nucleophile? Well, we have to assume it is in this case, of course, because we're not talking about competition yet. So the ammonia attacks the carbon because look at all those oxygens. Remember when we were talking about the strength of acids? And the more oxygens you have attached to the carbon, attached to the central atom, the stronger the acid, because they draw electron density away from that bond with the hydrogen. Hydrogen is free to go. So think of it that way. We've got these three oxygens there pulling electrons away from that carbon, which makes it slightly positive. It's an electrophile. So that makes it more tempting, more tasty for the ammonia to attack. And then you look at the leaving group. I mean, is that methyl sulfate anion a stable leaving group? Well, yeah. Look at what we can do with that negative charge. It can shift over to the other oxygen and it shift over to this one. Remember the resonance stabilization? All right, it can resonate to its heart content and be just as stable as any non-charged species. And since we formed a bond with that carbon, and we still have the three hydrogens and four bonds, whenever you have four bonds on a nitrogen, it's going to have a positive charge, right? And I go back to the ammonium polyatomic ion. It's got four hydrogens. It's got four bonds. It's going to be positive. So are we still balanced though in charges? Well, the top one we started off with a negative, we ended up with a negative. Bottom one we started off with neutral, but we ended up with a positive and a negative. So we're neutral still. That's an SN2 type reaction. Bimolecular nucleophilic substitution. All right. If this helps, Gibbs free energy of the reactants beforehand and the products after, we find that the products are at a lower energy. And we can prove that in the lab. It's just maybe it's helpful, maybe it's not. So we're going to take a short look at the substrate to see if the substrate, what makes the substrate a target for the nucleophile. And the substrate is always the one with the leaving group, right? That just goes without saying. This leaving groups are relatively stable with a negative charge. If that's the case, then they make a good leaving group. Leaving groups are typically conjugate bases of strong acids, right? So when we have this this methyl sulfate separated and it's a negative charge, even if it's in aqueous solution, it does not want a proton. Right? That makes it it makes it a weak base. Strong acids make weak conjugate bases. And this is a weak conjugate base. So it's going to be stable for that reason also, because it's not looking for hydrogens. Right? There are lots of hydrogens around there. Even if this is not aqueous solution, it's got hydrogens all over that other species. But it's not a strong enough base to attack those hydrogens. That makes it a good leaving group also. And a nucleophile, now we're looking at the other side. Nucleophile tends to be attracted by and form a bond to an atom that bears a partial or full positive charge. Does that carbon bear a partial or full positive charge? Well, if we look at its, let's see, it has 4, 1, 2, 3, 4. So it has a 0 formal charge. So we have to look at it from another angle. What is it attached to? It's attached to all those oxygens. And they're drawing electron density away from that carbon. Now, the methyl groups are feeding electrons into that carbon, right? We know that, but it's not enough to overcome the attraction of the oxygens that makes that carbon positive. Okay. And we do have, okay, we're talking about inductive effect there for the substrate potential leaving group. It has a very large inductive effect because of all the oxygens. And then once it leaves, it's resonance stabilized. And so we have that going for us. And those characteristics of the substrate make it a good electrophile. In other words, a good substrate for a nucleophilic attack. Okay, what makes a good nucleophile? They generally have an atom with these features: full negative charge, right? That goes without saying. If it's a full negative charge, it's going to be out, it's going to be looking for business. A partial negative charge, you could get away with that if the substrate is correct. And if it has a lone pair of electrons, even if it doesn't have a charge, if it's got a lone pair of electrons, then it's a nucleophile. So, for instance, our hydroxide ion, our ammonia has the lone pair. It's not charged, but it has the lone pair. And then what was that? What did they call that? That other one? The NH2 minus.
Inside or
Let me go back.
as enough?
Azonide. Azonide anion. That goes one step further than ammonia. Now it's got a negative charge plus lone pairs. It makes it a very, very powerful nucleophile. So these are lists of commonly negatively charged nucleophiles, and it depends on the circumstance as to whether they're going to do that type of reaction. Right, I'll leave that to you because I'm not sure how to name every one of them. Okay, can methane act as a nucleophile in an SN2 step? Let's look at methane. That carbon has no lone pairs and it's not charged. So that tells me that it would not be a good candidate as a nucleophile. All right. We're going to compare proton transfer and SN2 step. All right. Well, again, an electrophile is electron poor, a nucleophile is electron rich. And we have that in both instances here. An acid-base reaction, of course, is simply a proton transfer. And we know that. And that base is a good nucleophile, and the acid is a good electrophile. Right? But we're taking it one step further if we say that in the SN2 reaction, we're treating the hydroxide ion as a nucleophile rather than a base. But if you get down there small enough to be a neighbor to an electron, the electron doesn't care, right? We're just subdividing these into different types of reactions to try to, pigeonhole them and make sense of them. That's the way I look at it. In the end, the electrons just do what they're going to do. All right, draw the SN2 step that would occur between. Let's see if we can stump the band here. So C6H5, which is a benzene ring. Benzene ring, and off that we have a CH2I. CH2I. Okay, and then the other one is CH3SNA. CH3SNA. Okay, we need to simplify. This is a spectator, yes. So these electrons are going to go over here. Now, the question is, how many electrons should there be over there? I look at sulfur like oxygen. It's in the same group as oxygen. It would have started out like this and like that with that bond. And then that bond would add two more. So that should give us, let's see, sulfur is 6. Sulfur is 6 electrons with the 6 valence electrons. 1, 2, 3, 4, 5, 6, and then 7. So it's a -1 charge. Okay, that makes it the nucleophile. All right, so what part of this molecule is going to be positively charged? Well, this iodide would make a good leaving group, right? Wouldn't it? This would be very stable. In fact, it would be more stable than bromide because it's bigger. And you can spread that negative charge out over more volume. So this would be a good leaving group. All right, so one of these lone pairs is going to attack that carbon because it's slightly positive because of this electronegativity. So that lone pair is going to attack that carbon. This pair is going to go here, and that gives us that. And it also bonds, let's see, they want the final product. Let's see if we can do that. Okay, we've got this carbon. It's got its hydrogens. And then we're going to form the bond with the sulfur. Okay, so that should be our product. We have substituted this group for that leaving group right there. That's what we're doing. Okay, let's see. And yeah, we're good. I had to orient myself to a simple line drawing. Okay. We're still SN2, I think. Bond formation, coordination and bond breaking, heterolysis steps. Okay. Remember, excuse me. Remember our definition of a coordinate covalent bond. It's a covalent bond that forms from the donation of both of the electron pair for the bond formation comes from one species. So in that first case, that nucleophile, that well, Lewis base is accurate also. A Lewis base is an electron donor. So one of those lone pairs from the bromide attacks the carbon, which is the electrophile. The nucleophile attacks the electrophile and forms a coordinate covalent bond. In other words, both of the electrons come from the bromine. And it attacks that species because it's positively charged. It's an electrophile. It's actually a carbocation, a tertiary carbocation, because it has three other carbons attached to it. Makes it very stable. It's a very stable, positively charged species, which makes it ripe for the picking from the bromide ion. And they're calling it a coordination step in a series of elementary steps. This would be a coordination step where you form the bond where both electrons come from one side. We can also do it with this species down here, which would have been, let's see. Well, if it didn't have chlorine, if it had a methyl group in there, it'd be acetone. Okay. I'm not going to dwell on that for right now. Is the aluminum a good electrophile? The chloride is a good nucleophile because it has lone pairs. But why is it attacking that aluminum? Well, for one thing, aluminum wants to give up electrons. It's a metal. Plus, it's got three chlorides attached to it, and they're electron withdrawing. So that aluminum is going to be on the positive side. Okay, so that makes sense. But any bond that forms with that aluminum, the electrons have to come from the chlorine, both of them. So that's another coordination step. But when we do that, those electrons make that aluminum positive now. Let's see, aluminum would be 1, 2, 3, and then we have 1, 2, 3, 4. Yeah, 3 minus 4 is minus 1. So aluminum is a negative charge now. And the chloride is, let's see, chlorine is 7, and we have 1, 2, 3, 4, 5, 6. 7 minus 6 is plus 1. So the chlorine is a formal charge of plus 1. Okay? But that's a coordination step because of the way the bond was formed. We didn't kick anything off, right? There was no leaving group involved. It was just forming the bond. Okay. And this was, let's see, yeah, coordination step. A heterolytic bond dissociation or heterolysis is one in which the bond breaks and both electrons go with the leaving group. So when that first one, when we break the bond between the cyclohexane and the iodine, both electrons go to the iodine, which makes sense. And we're left behind with a cyclohexyl carbocation and the iodide. Heterolysis means other. That is, in this case, both electrons go one direction. And we can look at also this other group. Did that come from the previous slide? Yeah, I thought it looked familiar. Okay. Now we did a coordination, And now what can happen is the bond, a heterolytic bond can break between the carbon and the chlorine. And that gives that aluminum chloride anion plus the carbocation. That carbocation, I don't think is going to be very stable. So something's got to happen afterwards. Anyway, that's heterolysis as opposed to homolysis. Are they going to talk about homolysis too? No. All right. Homolysis would be like, best example I can think of homolysis is your acne wash often has benzoyl peroxide. Okay, so it's got this one, that one, so this one, and like that. That's benzoyl peroxide. And no, it's not. I left out an oxygen. There we go. There we go. That's benzoyl peroxide. Here's the peroxide. This would be when it hits your body, that's just enough energy, because this is a very weak bond, just enough energy to break that. And it produces this hold on a second, I'll get it. Free radical by a homolysis. So when this bond breaks, this one electron goes this way, right? Half arrow, and the other electron goes this way, half arrow. What you get is this species well, it already had, let's see, it had 2. So now it has only 5. It's a free radical because it has an unpaired electron. That makes it extremely reactive and deadly to bacteria. So that's how it kills the bacteria in your pores without doing too much damage to your cells. In fact, let's see, what is panoxyl is my favorite. I'm allergic to those aluminum containing antiperspirants. And the deodorants that don't have that in there, they give me carbuncles. So I don't use any of those. I use panoxyl after the shower and wash it off, and it leaves a residue behind, and it kills the odor causing bacteria. I hope. You can't smell me from there, can you? Okay. So that was my solution to my medical problems. That's homolysis, where the electrons divide. And we used a half barbed arrow to show that. Okay, back to the slides. Nucleophilic addition and nucleophilic elimination steps. Okay, so if we have a nucleophilic addition, it's simply the formation of a bond with the nucleophilic attacker. And that's why we introduced the coordination step. So you see that this nucleophile, this carbanion, is attacking that carbon, which is slightly positive because the I can't remember those words. Inductive effect. I'm gonna have to work on that. The inductive effect of withdrawing electron density away from the carbon makes it slightly positive. That nucleophile attacks the carbon and forms a bond. And by breaking, in other notice that when that nucleophile attacks the carbon, if the bond were allowed to stay with nothing else happening, that carbon would exceed the octet. You can't do that with carbon. Carbon has nowhere for those extra electrons to go because it doesn't have access to d orbitals, right? It's in the second row, and you can't have two Ds. You can only have three Ds. That's why if you want to exceed the octet, you got to move down to at least the third. Okay, so because we can't have exceed the octet for that carbon, what gives is the pi bond breaks with oxygen, and those electrons are transferred to the oxygen because it can accommodate three pairs of electrons. Okay. Another nucleophilic addition. Okay. Water, right? Because the oxygen has lone pairs, can attack the carbon. I got to figure out what that. I know it. I knew that name one time. What that compound is. Acetyl chloride. That's it. Because let's see. That's the acetate polyatomic ion. We can just add there acetyl chloride. Okay, I'm happy now. So again, the carbon is deficient. The water has excess, has lone pairs, and forms a coordinates with the carbon, and we have to break the double bond again. We have a strong base, strong with lone pairs, and the carbon in that methyl cyanide is slightly positive, principally because of the effect of electronegativity. And the nitrogen is more electronegative than carbon. Yeah. So that's why it's drawing electron density away from that carbon. It's not much. It's not very positive. But the hydroxyl is extremely nucleophilic. So it's strong enough to make the bond. And when it does, we have to break a pi bond in order to preserve the octet for carbon. So carbon now only has 4 bonds in the product. And actually, we should be able to resonate with that nitrogen and the oxygen. We can get a proton transfer within an intramolecular proton transfer, and you can resonate. But we haven't got there yet. Maybe we will. Okay. So we're taking all of those real examples and condensing them into a theoretical. So we got the nucleophile attacking that carbon, which is slightly positive, and we have to break the bond with the Z to preserve the octet. So that was nucleophilic addition. The next slide must be elimination. Well, wait a minute. We didn't eliminate anything in this one, did we? No. When we say elimination, we have to have a leaving group go somewhere, right? So we're only talking about nucleophilic addition in this slide. More examples of nucleophile elimination steps. All right. We have seen eliminations during the substitution reactions. Okay. Now it makes sense. In this case, If we have this particular species where we have oxygen is positively charged, negatively charged, excess electrons, but the chloride makes a very good leaving group. So the chloride, if the chloride leaves, then carbon is more stable with 4 bonds. So the oxygen makes a pi bond and restores the octet for the carbon and gives us acetone. Okay. That's an elimination step. Why do they call it nucleophile elimination? I'm not sure. I have to read the text. Okay, so the second example, what's a good leaving group? Water. Water's excellent leaving group. If you can kick water off as a leaving group, then it's guaranteed reaction. Water's an excellent leaving group. So when water eliminates, right, it breaks that bond, takes the pair with it. Then the amide has to form a pi bond in order to restore the octet for the carbon. But the positive charge stays behind. All right, we're still balanced. Started off with a positive charge, now the positive charge is on the nitrogen. Okay. All right. The introduction of those elimination steps was so that we could talk about this elementary reaction step, bimolecular elimination. So again, we have the two, but now it's an elimination process. Bimolecular elimination requires 2 species to interact with each other. And in our example, we have this strong base, this hydroxyl, attacks the hydrogen. And when it forms the bond, it coordinates with the hydrogen, then the bond with the hydrogen and the cyclohexane breaks. And it forms a double bond to preserve the octet with the carbons. But as a consequence, now we have a good leaving group in the bromine. Right, so that bond breaks. And we've got 3 arrows there, so we haven't violated the 3-arrow rule. I think everybody missed that one. And that's the only reason for the 3-arrow rule is to keep students and actually scientists from going overboard. Right? You want your reaction to be from here to here, and how am I going to get there? Well, look, if I use 6 arrows, I can get there in 1 step. Right? So we're saying, as a practical matter, 3 arrows is it. Okay, and we end up with a double bond, and the elimination product is the leaving group, bromine. But we had a bimolecular procedure. We had to have the substrate plus the nucleophile attack that hydrogen. Let's see. Okay, this only works if the leaving group is on an adjacent carbon. Yeah, the hydrogen in the leaving group must be attached to the adjacent carbons in order for this to work. If well, in this case, there are hydrogens all around. So where else could it attack? It could attack the hydrogen on the bottom, right? But it would be the same reaction, essentially. Okay. Examples. Let's see. There's our leaving group. How do we identify that leaving group? Well, it's the one that would be most stable, right? Yeah, that tertiary amine compound, right? You got three methyl groups attached to the nitrogen. That's a tertiary nitrogen. Is very stable leaving group. So what's going to attack? Well, we're gonna send a strong base in there again to attack the hydrogen. If we use a strong base like that, like hydroxyls, then it typically goes after hydrogens. I mean, it can go after carbons, but in this case, since the leaving group is on the beta carbon and the hydrogen's on the alpha carbon, it's more likely to do an E2 elimination. And by picking up a hydrogen, we're forming, now water in this case is not the leaving group, but it is very stable nonetheless. And the double bond then is formed on the carbon C1 and C2, between C1 and C2. What would the name of that compound be? 1, 2, 3, 4, 5. Be pentane. Actually, it's pent 1 ene and 1, 2, 3, 3 methyl.
Yeah.
It's good practice. Okay, so another example. We have this 1-bromoethene. Yeah, 1-bromoethene being attacked by that weird name compound, that anion. Azonide. Azonide. I have to say it over and over again to drill it into my head. Azonide ion attacks one of the hydrogens. And when the bond breaks, those electrons have to go somewhere, so they go into the pi bond. And then the bromine has to leave. And it's good that it leaves because, well, it's an excellent leaving group, plus we can't exceed the octet on the carbons. So we form acetylene, actually. I don't know if that's the way they do it industrially, but it could be done that way. And then you fill your, we used to get tanks about this big, kind of fat, squat acetylene tanks. And there would be acetone in the bottom, about that much. And the acetylene would be dissolved in it. If you have pure acetone in a compressed tank, it's very hazardous. This way, if it's dissolved in the acetone, it's released slowly rather than rapidly. And you don't want it to come into contact with copper because the polymerization that occurs is extremely exothermic. It would blow the pipe up and probably translate back to the tank. So all the piping that we had built into the lab for our acetylene was cast iron. Yep, cast iron all the way to the atomic absorption spectrophotometer. Do y'all use one of those? Or maybe one? No, you'd have to have a flame, right? You don't have flames. Okay, so you don't have one of those. That's okay. They're really only good for metal analysis. And any type of metals you analyze for are in ionic state, right? They're in plasma.
Yeah, we don't do them in regular
Oh, okay.
copper or anything like that gets sent out to the pipe cord.
Oh, okay. Okay. They have pretty quick turnaround too.
Yeah, it's not bad.
Yeah.
lot of stuff that we send out.
Have you ever had to send any out for quick turnaround staff?
Well, we can't really call it staff.
No.
Just say, I mean, cause some of the stuff, like there's, a seizure medication that
Uh-huh.
we used to run in-house and we're not doing it in-house anymore, cause we're only doing like maybe 10 a year, so it's not worth
Yeah,
our time and money to do it in-house. So
yeah.
that's been a little aggravating for some people because they've been used to having it
Uh-huh.
right then when they do order it, but now it's just depends 1 to 3 days. That's all I can say.
Okay, back to our topics. So identifying the electron rich and the electron poor sites is not just good for E2 steps. It's also good for any other type of reaction you're going to try to propose an elementary step. Remember, these are elementary steps. These are not overall reactions. Like we're saying, in this one step, we're going from here to here. If we have a proposed product from a reaction, it may take 3, 4, 5, or 6 elementary steps to get there. And they might occur within that arrow, or some of them may occur here, and then you modify it, and then some more of them occur. Right? So that gets to the next semester when we multi-step reactions. Okay, back to this slide. The base is going to be electron rich. That's just given. A Lewis base has lone pairs available to donate. So that's the nucleophile. The electron poor, in this case, is the carbon atom. But why is it electron poor? Well, it has to be bound to the leaving group. In order for the E2 reaction to occur, the attack has to occur on the beta carbon hydrogen, and then the leaving group has to leave from the alpha carbon. Oh, wait a minute, did I get that turned around? Well, they have to be on adjacent carbons. Okay. So this is the model for the E2 reaction. Bimolecular elimination. Okay. Next is electrophilic addition. Is it electrophilic addition or elimination? We've talked about the bimolecular elimination. If we have, and in this case now, the electrophile is going to attack the substrate. The electron poor species now, this electrophilic addition occurs as a bimolecular process where the electron poor species attacks the nucleophile. The nucleophile has to have extra electrons. And very often what you'll find is the extra electrons are contained in pi bonds because they're not as strongly attached. You know, they have to go off axis to get their bonding, and they're out there exposed. One thing that can get in the way is if they're sterically hindered. But in this case, we've only got methyl groups in there. So if the electrophile is small enough, it can get in there and form the bond. Okay. So in this case, what we're forming by breaking that pi bond, forming a coordinate bond with the electrophile, then that makes that one of those carbons, in this case, the carbon on the right, it makes it deficient. Right? It's only got 6, well, actually, 4 minus 3 is +1. So now it's a carbocation, right? The question is, in this reaction, how stable is that carbocation? Did I talk about this before? Stability of carbocations. This one, right? A methyl carbocation is very unstable. You never see those. This one, where we have another methyl group on this side and like that, is more stable. Okay. If we take one of those hydrogens away and put another methyl group in here and one here, that is even more stable. And the most stable are the tertiary carbocations, where we have like that, 3 methyl groups attached to it. That's very stable. So how stable is this one? Well, it's 1, 2, 3. Right, it's very stable. Yeah, it has 3 carbons attached to that positively charged carbon. That is extremely stable, and the reason for it is the and I'm searching for that word again. No, not that one. The one where we move electrons into neighbor. Huh?
You just said it a few minutes ago.
Oh, I might have to write it down.
I'm saying induced.
No, I'm gonna look it up and write it down. There it is. Inductive effect. That's close. Yeah, very close.
You really wrote it down.
There we go. Okay. Wait a minute. I skipped one, didn't I? Ooh, I skipped several. Okay. Now we're saying that the carbocation is unstable, but relative to other carbocations, that is the most stable type, right? So the product in this case is a carbocation, which means that it will react with something else because it lacks an octet. But it's stable enough so that it exists long enough so that it can participate in another step. Okay. So in this case, we've got, what do we have? We have dimethyl acetane. Let's see. I hate this happens. Let me get a drink. Let me get a drink. Dimethylacetylene, okay, is electron rich. So it is the nucleophile attacking the electrophile, hydrogen. It forms a bond. Yeah, forms a bond, but since it makes a bond with the hydrogen now from one of those pi bonds, then the neighboring carbon is deficient. Now, it will do that because chloride is a good leaving group. But it's more reactive than it would be like this reactive right here. Except that it's kind of in between. And the reason I say that is that carbocation is, let's see, primary, secondary, tertiary, quaternary. Wait a minute. No, primary. This is primary because it's got 1. Secondary, tertiary. This one is the analog to that one, only it's got a double bond in it. And that gives it an effective electronegativity, which provides electrons to that carbocation, stabilizing it. So it's somewhere in between here. Okay. Electrophilic addition step for benzene. Right? Benzene has the double bonds, although I guess this reaction could occur. We could form that bond with the not the cation, NO2 cation. But that one's a stretch for me because benzene rings are extremely stable. Right? You typically don't break that bond unless that NO2 is not just positive, but it's extremely positive. All right, so I guess theoretically it could happen. It's just I wouldn't expect to see it. Maybe if we increase the concentration of NO2 plus to astronomical heights, then the chances of the reaction would increase. Okay.
What about heat or freezing it,
Freezing it?
heating it?
Probably heating it. Yeah. Yeah, then you would then those electrons in the pi ring, yeah, would be more active. That's possible. Yeah. That could be, yeah. You could that plus you might have other ingredients you add there to enhance the reaction. I don't know. Okay, so I'm gonna give them that one.
But they still need more though, like you said.
Yeah, you need something to make that bond break. Okay. All right, carbocations are typically unstable. Okay, so the reverse electrophilic addition is also a common elementary step. Right, so it can go backwards as well as forward. It depends. If the leaving group, that E, is very stable as a cation, then the reverse reaction would be possible. Okay. All right. Now this one, okay, I'll give them this one, where we have the sulfate. The sulfate group attached to the carbon is a good leaving group, and that that carbocation really wants to make its octet.
Yeah.
And when it does, it forms the aromatic ring, which is extremely stable. Right. So that actually works from both directions. The sulfate cation is very stable because of resonance, and the nitrobenzene is very stable because of it forms a aromatic, which is very stable. Right. So I like that one. Yeah. Now, this other possibility where we had the tertiary carbocation as a consequence of one reaction. In an aqueous medium, water can attack a hydrogen and reestablish that double bond methylpropene. And this would form an acid. So I'm wondering what kind of environment would promote the formation of the hydronium ion. That's what's happening right there. That's hydronium. Right? If you had an acidic solution, you'd already have a bunch of hydroniums in there, right? And the equilibrium would tend to shift back the other direction. So I'm thinking if you do this what would happen no, you wouldn't want to use basic, you wouldn't want to put hydroxyls in there because then they would compete. But that might work too, right? If you put a hydroxyl instead of water, then it would definitely go for, which hydrogen would it go for? Probably go for that one. Yeah. So maybe they're using water for control. You don't want the reaction to be too violent, too, right? You might get too many side reactions. Anyway, that's a possibility also. And that's just a reverse reaction of the previous one we showed. And the reason it does that is that carbocations are unstable. This is relative stability, but even down here, that's very unstable. Okay. All right. Previously, we mentioned movement of hydrogens within a molecule. That's a hydride shift. In this case, the hydride shift is not the way we were thinking of it in that resonance, where it would be hydroxyl versus sulfhydryl back and forth. That does happen. But in a hydride shift, we're talking about moving a hydrogen from one carbon to the other. And when we do that, we're looking for stability. Right? If we have a carbocation, a secondary carbocation, and we have the ability to move a hydrogen over there and shift the positive charge to a tertiary carbon, that would be preferred. That reaction will be favorable. Yeah. So that's a 1,2 hydride shift. Now, what it, what that arrow is showing us is actually two things happening at once. The bond is breaking, but a pair of electrons are going with that hydrogen over to the carbon. So two things are happening there. You know, that's I don't know if that's against the rules or not. I guess not. But we do want to focus our attention on this one rule. Hydrogens, protons, hydrogens never exist by themselves in any chemical reaction. They're always attached to something. So that's why we have to draw that arrow and be sure that we're not leaving that hydrogen out. We wouldn't send the hydrogen, we wouldn't do this. Let's see. Hydrogen and methyl group. And then that hydrogen. We wouldn't do this. We'd say break that bond and make that. And then do this. That never happens. Now we simplified, remember we simplified our compounds with reactive hydrogens on them to show this as a reactive species, but in reality, it's always attached to something. What was it? The lithium hydrides, aluminum hydride, right? We simplified those to this, but that doesn't happen. Not in real life. They're always attached to something. Okay, so this is a 1,2 hydride shift. A 1,2 methyl shift is similar, only instead of the hydrogen now, it's a methyl group that moves. And we're still trying to stabilize the, well, actually, in this case, yeah, okay. In this case, we're doing the same thing. We're converting a secondary carbocation to a tertiary carbocation by that methyl shift. Okay. Now, in this case, we could do a separate, we could do that methyl group, although I don't think it happens that way. We could do the methyl group like this and like that. That would give it like that. And then it would attack here. But that's unlikely too. Because just like carbocations are unstable as a positive charge on a single carbon, a negative charge on a single carbon is also unstable. Okay. What makes chemical reactions go? Well, in the simplest terms, products are favored over reactants. There's some reason. Maybe it's they're lower energy, right? More stable. Lower energy is a good driving force. What we want to look at for organic chemistry is stability. Are the products stable? Right. So, and that very often refers to the stability of charges or lone pair electrons. So in this case, we have a bromide and a tertiary carbocation. And if we coordinate that bromine with the positively charged carbon, then we get a more stable situation. It has greater stability simply because we don't have excess charge. If we can move to a neutral situation, then that is a stabilizing force. We can talk about charge stability versus bond energy. And they can be similar concepts and they can be different. If we look at this reaction on the left, the negative charge is better accommodated on the chloride than it is on the amide. So that's an example of charge stability. And if we look at the equilibrium constant from that, it's massive, right? 10 to the 43rd. So that gives us another piece of information that tells us this reaction is definitely going to the right. If we're looking at bond energies only, and we're interested in the strength of the bonds, then in this case, bond energy would favor reactants, but charge stability favors products. Then the question is, which one wins? Charge stability usually wins rather than bond energy. That's the whole point of this slide. When you're looking at charge stability versus bond energy as a stabilizing force, low bond energy would be stabilizing. Bond energy on the left is more stable than on the right, but charge stability is greater for the right. So when you have to flip a coin, it comes down on the side of charge stability. In this case, in this example reaction, we're saying that charge stability favors the products, of course, bond energy favors the reactants. And they don't give us a K value for this one. Yeah, charge stability is better for the right. Chloride is more stable than hydroxide as far as charge stability goes. And well, there it is. Oh, okay. I've sort of given you an introduction to this one. Carbocations and charge stability. All right. It also, actually, I gave you only part of the story. Charge stability for substituted carbons increases as you substitute the carbocation with more carbon attachments. Okay, but if you can introduce resonance, then that will also stabilize a carbocation. So if you have this An allyl cation is one in which you've got three carbons, actually a single bond adjacent to a double bond on carbons. That's an allyl. Here's another mouthful, oxocarbenium ion. So, which is more stable? Well, the allyl cation, 6 of one, half a dozen, right? It shifts back and forth with equal resonance. For the oxocarbenium ion, I would think the more stable would be the left-hand carbocation. But since it resonates, that does stabilize both of them. And then the benzyl cation, there are other resonance structures here. Yeah, we can resonate that carbocation around the benzene ring. And if we put the carbocation on the benzene ring, that also tends to stabilize it. Resonance stabilization is what we're after here. All right, I mentioned this one already. And the reason that the carbocations increase in stability to the right is that inductive concept, right? The methyl groups or R groups with carbons on them, they tend to funnel electron density toward the cation. And the more of them you have, the more stable that cation can be. Okay, we introduce other types of cations. Stability, the least stable is the methyl cation. And then between the secondary and the tertiary carbocations, you have allyl. Well, actually, it's saying the allyl is about as stable as the secondary. And the tertiary is about as stable as the oxycarbenium and the benzyl. And the reason for that is that not by induction, but resonance stabilization. Yep. Which side of this carbocation rearrangement is favored? Let's see. Okay, what are we looking at here? We're looking at a methyl shift, a 1,2 methyl shift. Yeah. So, which one is more stable? Well, let's see. On the left, you have a 1, 2, 3, a tertiary carbocation, and on the right, you have a secondary. So I think the one on the left is more stable. Change on reactants, carbocation rates, favor the reactant side. Favor the reactant side. So while you could have that 1,2 methyl shift, it's more likely that it's going to stay on the left-hand side. That carbocation is more stable. Okay. So another way of looking at carbocation stability is with the idea of conjugation. If we have a methyl here, right? Methyl group under A, we have an empty atomic orbital, right? An empty atomic orbital that is effectively isolated. If, on the other hand, we put that empty atomic orbital, which was a p orbital, on the carbon boat. Next door, we have a methyl group. Okay, look at that in terms of stabilizing effect in a molecular orbital bonding situation. Okay, remember how we construct molecular orbitals? We take the separate, actually, when we were looking originally at hydrogen and hydrogen here on the energy scale, we had a 1s orbital here. Remember this diagram, 1s? Then we had bonding and anti-bonding here. And so this is sigma 1s, and this is sigma star 1s, like that, like that, like that. So we put both of those electrons down here. That makes for a bond order of 1, a stable situation. What they're trying to do here is use molecular orbital theory to explain the stability of a carbocation, where instead of separate atoms coming together, we've got separate parts of a molecule interacting. And so if we have atomic orbital on the, actually they're blending. They're blending molecular orbital theory with valence bond theory. And organic chemists do that a lot. So on the right, that right-hand carbon, the carbocation is an empty p orbital. And on the left, we have a molecular orbital in which the carbon is bonded to a hydrogen at lower energy. Then when we combine the two, we get a bonding and anti-bonding. And both of those electrons from the left-hand side now move into the molecular orbital and lowers the energy. Does that make sense? So by simply adding one carbon attached to the carbocation, we have stabilized by what they call hyperconjugation. Let's see, are we going to go to secondaries? Not yet. But we could continue that, right? We could add others around it, and that would lower the energy even further. But that's not part of our slide set, so we won't go there. We're only going to use molecular orbital theory when it suits us, when it helps explain things. Otherwise, valence bond seems to work just fine. Okay. When we talk about resonance stabilization, there's another special kind. It's called keto-enol tautomerization. If we have a ketone, right, where we have ketone is always like this. We have a carbon group there and a carbon group there. That's a ketone. So that's what the left-hand one is showing. If under the right conditions, and it can either be basic or acidic, we can form an alkene. We can move this double bond to one side or the other. And that gives us like that. This is called an enol, right? Alcohol and enol. This is keto, this is enol. And these can resonate back and forth. That also tends to stabilize. Now, depending on these R groups, one or the other might be more favored to. But you still get some of the enol and the keto together. Okay. These are called tautomers. Don't ask me why. Okay, so what we're trying to show in this mechanism is the process, the elementary steps that lead to keto versus enol. With a proton transfer, if this is in basic solution, the top one is in basic solution, the bottom one's in acidic solution. If in basic solution, what we're going to get is the hydroxyl is attacking the hydrogen on neighboring carbon to the ketone. And that produces a carbanion. Then we shift electrons into a double bond between the carbons. And now we've got 5 bonds to a carbon. So we've got to break one of those pi bonds and produces an enolate anion. And then we get a proton transfer from proton transfer. Where does the proton come from? It must come from water. They're not showing us that. Proton transfer then comes from water. Oh yeah, there it is. Okay. So we see that on the enolate anion attacks water and reconstitutes the hydroxyl. So the hydroxyl is almost like a catalyst because it goes in one end, comes out the other. Okay. So that's how you go from a keto to an enol in basic solution. In acidic solution, instead of a hydroxyl attacking, now we have the oxygen lone pair attacking the hydronium ion, right? Which makes sense because the hydronium wants to give up that hydrogen. Remember the equilibrium constant for this reaction. And minus 14. So if you've got this one there, it's ready to give up that hydrogen. So that's what it does. The oxygen, the lone pair from an oxygen attacks the hydrogen. It recreates water, and that oxycation then does it has to break the double bond between oxygen and carbon in order to reestablish, to neutralize the positive charge on the oxygen. But that creates a carbocation. And then we get the water attacking the hydrogen on the secondary carbon, on the neighboring carbon, and reconstituting the double bond. That one, we looked at that one earlier, I think. It wasn't exactly like that though, because there was a leaving group. Okay, so this is a different type of reaction. It's simply 2 proton transfers. That's all it's required to tautomerize a keto to an enol. It's just 2 proton transfers. All right, why do I have the same slide? Basic. I don't see any difference. Why do I have 2 slides in there? Yours doesn't have it? Does it have 2 slides like that? Oh, yeah. This is the reverse reaction. Okay, going from enol to keto. Okay. Again, it's 2 proton transfers. All right. Messing with my head. Okay, we ought to be getting close to the 3 more slides. Okay. Let me get my bearings here. Hold on a second. Let me see. Okay, we are going to, okay, that comes later. We've introduced, what reactions have we looked at so far? We've looked at, proton transfer. Right, then we came to SN2 and E2. We did coordination steps. And then we advanced that somewhat with these hydrogen transfers to a keto-enol tautomerization. We haven't talked about SN1s and the E1s. We'll do that, not for this exam, but for the next one. Yeah. And then that will give you most of the elementary steps that you'll ever encounter. Okay. I mentioned earlier the stability of keto versus enol, and it would affect the proportions. The one that gives us the greatest increase is the second one in this list. But all of them have very minor enol components. Most of them are keto. So what that tells me that keto is the much more stable form. Now, the reason that we would want to know keto versus enol, if we have enol available, then that sets up the ability to send the reaction a certain direction that the keto would not. It might be a small amount, but if we've got enough reactant, then we can bleed off that one and it keeps feeding us. You know, the equilibrium shift would give us enough enols to complete the reaction. There it is. Keto form is generally favored. It doesn't stem from a difference in charge stability, but rather an outcome of a greater total bond energy in the keto form. So in this case, the bond energy wins versus the charge stabilization. Well, because there is no charge. So the keto is more favored. And remember, we're talking about total bond energies. The higher bond energy, what does bond energy mean? Let's go back to general chemistry. When a value is listed as bond energy, that's the amount, they're always positive values. That's the amount of energy required to break the bond. So the keto side would take more energy to break those three bonds. The carbon, hydrogen, carbon, carbon, and carbon, oxygen. It would take 1,477 kilojoules to break that bond. Whereas the enol side, we add up all of those individuals and we only need 1,430 kilojoules to break those bonds. They're less stable. So the larger number, bond energy is more stable. Okay. Glycolysis. Y'all going to take biochemistry at some point? Okay.
I think so.
If you did, you'd learn the steps in glycolysis. And that's the original, that's the first thing that happens to glucose in your body is glycolysis. And it's anaerobic. In other words, it doesn't need oxygen. So if you're exercising and you exceed the oxygen intake levels of your muscles, then it's going to shift to glycolysis only. And then in order to reduce the toxicity of the products of glycolysis, it converts, which one does it convert? I don't see it there. It converts one of the products into lactic acid. because it's less toxic, but it hurts. Okay, that's enough of that. Let's see, how we doing on time? 11:20. Oh, good, we got time for lab. But Olivia's going to miss out. And we don't record it. Well, I can record a discussion first on. Do that. I think that would be helpful. Lab 3.
Make it up.
Huh?
Is she gonna try to make it up?
I don't see how. Lab 3, this is recrystallization. As a purification technique, and we're going to recrystallization of benzoic acid. Now, the benzoic acid that we have in the lab is relatively pure. So I wouldn't expect the difference between what you put into the procedure and the amount of benzoic acid you get out is probably going to be losses. Right? It's not going to be losses of impure contaminants. It's going to be losses in the procedure itself, which is okay. But if we were to analyze it with sensitive enough equipment, we probably would find that our benzoic is not 100% pure, especially since it doesn't say reagent grade, it says lab grade. So it probably does have some impurities in it. The idea is that you've got the benzoic acid plus impurities together, right? And then you dissolve them in water so that the concentration is high. In water produces high concentration. In fact, saturated. That's what you want. Saturated at any given temperature. And we're going to saturate in boiling water. So boiling water can hold a lot more. And then as it cools, high concentration saturated in 100-degree water. And then as it cools, the benzoic acid crystallizes. Well, the idea is twofold. Benzoic acid is a much higher concentration, and the impurities have to be soluble also. Right? If they're not soluble, then why bother? Right? We could just filter it, right? Dissolve the benzoic acid and filter it, and all the contaminants will be removed. But if they're both soluble, then and we recrystallize from this saturated solution, the saturated part is the benzoic acid, and it's going to crystallize first because its solubility product is going to be higher. Plus, crystallization is best accomplished when you have crystals, seed crystals to begin with, and then the benzoic acid has something to latch on to. Right, so once you start crystallizing, then these attract benzoic acid and they don't attract impurities because the impurities don't fit into the crystal matrix. So you've got two avenues of purification here. And the slower you cool it, the bigger the crystals. Have you ever seen, I don't know what, copper sulfate crystals that have been grown very slowly? You can get huge blue crystals that are gorgeous. I used to have a device. Actually, I didn't have it. It was part of the school's high school. And it was a container with a heater in it. And it had a little motor that slowly rotated. And on the end of that motor was this two prongs. And on each prong, you could put a starter crystal. So you put a saturated solution at high temperature of copper sulfate in there. And then you lower that thing in there with crystals and it gradually move around, picking up. And the thermostat would be set to gradually decrease the temperature. So it would saturate, it would keep the solution saturated and the crystal would gradually grow on that thing. And the slower you grow them, the bigger the crystal. That's the theory behind flash freezing. If you flash freeze a biological material that has cells in it, then the ice crystals formed are very small. They're not big enough to poke through the plasma membranes of the cells. So that's why we used to take plant samples and dunk them in liquid nitrogen, freeze them so fast, and when you thaw them out, they don't turn into a mush. Well, actually, we didn't do that either. We took the frozen sample and put them in a freeze dryer and dehydrated it. But the idea is the slower you freeze it, the bigger the crystals. So if you freeze stuff in your refrigerator, in the freezer, then it's going to freeze slow. Crystals are going to be big. They're going to poke through cells. When you thaw it out, they're mushy. So the faster you freeze it, the better. Okay, so that's the basic concept behind what we're going to do. The devil's in the details. Yeah. And of course, once you get the crystals formed, then you filter it. And that leaves the impurities behind in solution. Okay. And then on the filter paper, you let it dry. So that means what? We probably need to weigh the filter paper ahead of time. Or weigh the filter paper and the Buchner funnel that it's in. That would be simpler. Right? Just weigh the whole thing. And then you wouldn't have to separate the crystals from the funnel to get your final mass.